Hey folks, Todd Coburn here, and today I wanted to talk about bolstering our foundation for accurate finite element analysis. And while there are probably a lot of great, more detailed and deep studies into finite element modeling at this particular conference, what I wanted to do was focus on the basics. And the reason for this is that I have found so many times folks that are generating finite element models that they don't understand, where they're misusing the elements, and they really don't have a feeling for whether their model has any representation of accuracy. And in order to counter that, I want to propose some ideas that are kind of dropping down to a more simple model and understanding how NASTRAN and the elements it uses work. So in order to make a good finite element model, not only do we need to be agile in the pre and post processor, we also need to understand the NASTRAN elements, which ones are being created, what are their limitations and idiosyncrasies, and how to leverage that so we get what we need in our model. So what I wanted to propose is dropping back down into the trenches of understanding what each NASTRAN element does, how it works, and then verifying it with little simple cases where we can actually check the results. So I'm going to show you a few of those examples. We'll kind of move fast and kind of just get a flavor for the kinds of things we can do in order to do a better job of understanding NASTRAN. Here are some of the best practices I have run into, just a few of them in what I have found, and we're going to look at a few of these as we go through our pitch today. So first, let's just take a look at rods. Rods are probably one of the very simplest of the NASTRAN elements, but before we use rods in our model, and there's a number of places where rods can and should be used in many practical finite element models, I wanted to look at the idea of understanding how that works. So what I'm basically suggesting, and some of you may be beyond this point already, but if you are making models, maybe with Patran, and haven't really worked with NASTRAN or understand how it works, to make a simple model of just a simple rod or series of rods. Keep it quite simple, like this little fixed free rod with a single axial load, and practice predicting the results. A model like this, we can easily predict what the results are, and we can predict from the applied loads what the stresses are. We can predict the deflections. We can predict other things. And if we compare that to the NASTRAN output, we then can gain some confidence in, oh, I used this element correctly. Now this is kind of almost a nonsensical example because it's such a simple element to use, but even using this element, creating a little model with it, predicting what it's going to do, and then checking your work will give us a feel for how this element works, so that when we use it in other applications of larger models, we can be confident that it works. And what I propose is that we do this with each and every element that exists in every model, whether it's a rod or a bar or a gap element or for a buckling analysis. We first start with a simple NASTRAN model of the simplest elements, predict its behavior, check its behavior, and then maybe make a more complicated model, maybe a few more elements, or maybe a larger piece of the substructure. While we start off with predictable and verifiable numbers, we make it bigger and bigger, and the predictions can still often be done, but the accuracy will be less and less, and we can start to see how the NASTRAN results begin to diverge from the accuracy that we can actually predict by hand. But then we have confidence because we've walked through many of those changes. We can see the trajectory and can be confident that it works. There are many other little nuances about rods that are kind of also require some care. We're going to save that for a later date. But just to kind of whet your taste buds on the foundational idea of creating a model, predicting the results, checking to make sure it works, and then expanding on that for each and every element as we before and as we go along creating our larger models. Okay, now these, when we have a model this simple, you can certainly make this in Patran, but these kind of models can easily be made just as a BDF text file. Feed that into NASTRAN. You can get really fast results that are understandable, easy to tweak. You can actually run a number of studies in just a few minutes or hours, and get a lot of confidence for how NASTRAN works. And then the next step is, if you're using like a Patran pre and post processor, is to go and read in that model or drop down a model from Patran, take a look at how that works, practice tweaking that model, bring it back in, and then look at how the results in Patran look versus your FO6 file where your written results are. This is a really good skill that every analyst, if you want to be a super user and can't do that, you are not a super user. Super users both understand NASTRAN and the pre and post processor. They don't just make complicated models. They understand the details and the foundational blocks that that more complicated model is constructed with. And when they go to a more complicated model, like a brick kind of element or something that is harder to predict, they have worked their way into it, so they're confident that they understand how that element works, the kind of results that comes out, which ones can be taken verbatim out of the results plotting in Patran or something, and which ones need some post-processing, because actually many or even most margins of safety for practical structures are going to need to be hand processed, because NASTRAN just cannot calculate in a reliable way the margins of safety that we need for practical analysis without a lot of very detailed and different finite element models for a given piece of structure. So another practical skill that we need to start with at the lowest most level is making free body diagrams. And one great free body diagram for understanding your NASTRAN results, and if you start with these little verification models first, practice making a free body diagram, you then can expand upon that. It will give you experience for making larger and larger and pulling substructure, free body diagrams, and so forth. Now, while it is true that Patran offers a section cut and free body diagram like tools, however, a lot of times if we just rely on those tools, we don't actually know what's going on and we aren't able to verify things. So when we drop down to an element by element kind of model, when we practice the skill of plotting those free body diagrams on the element, and then start practicing with larger and larger substructures, then we practice with Patran trying to do the same thing. It actually develops skills so that when we get into those models that are complex enough that we can't really do a great hand prediction, we've developed the confidence by building up to some level below that where we've had success in matching those. So a model like this, you grab your forces, your external forces, you grab your rod forces, and you start plotting them out on a node by node, element by element basis until everything is in equilibrium. And then you study the results and make sure that it's correct. C-bars and C-beams, these are another one of the more simple elements to use, but I've seen countless models where folks don't understand the moments of inertia and how those resist bending. The way they're aligned is not necessarily intuitive, the way all of us would think that should be. And so we find people that have flipped normals, bars that have one bar connected to another bar where the one moment of inertia switches to another plane and back again, panels that have the same problem. So understanding what NASTRAN bars and beams can do, what the stresses are that are reported, which stresses are not reported, and being ready to generate those as needed so that we can have make sure we have all the right margins of safety written for the structure. A little tool like this I have found is very useful, where we can put the nomenclature of the bar and beam element on it, so we can hold that, orient it with our model and our structure and how that goes, and make sure that when we're checking our model and checking the output and checking the results that we're getting out of Patran, the ones that we're post-processing, we can be sure that we're using those bar and beam elements correctly and reading those results correctly. Does that make sense? Another skill that's very useful is, in addition to that exploded free body diagram, is being able to plot your shears and moments, a shear and moment kind of diagram. So here's where that can be done for a simple bar element, for in this particular case, we're just looking at a single bar, but where we can take an exploded free body diagram, write the shears and moments on there, all of the element and reactionary forces, just like we did for rods a little bit ago, and then go and directly below those, plot a shear and moment diagram. This is very powerful for being able to look at a structure like a frame, a cross-sectional frame, and look at the shear and moments and axial loads on the frame and on the floor beam and struts, and quickly identify which spots are needed for additional hand analysis, and be confident that we have evaluated the critical loads and stresses for the model. And we can do this by hand on a simple model, and then if we run into it and need to plot that up, we can plot it up on a element or series of elements in a bigger model. Now, Patran actually has a great tool for doing this, but I recommend first we need to drop down and do it on an element by element basis with NASTRAN, the NASTRAN elements and output, and then as we graduate from that and get success in matching those, we can go and then plot in the Patran, the shear and moment tool in Patran, and then make sure those are looking correct, and then we can go on, and then when we have a more complicated structure that can be quite difficult to check on a larger basis, but you can still check it on that smaller basis. We have confidence that what we're seeing, that we understand how those elements work, how the tool works, and that we're getting a correct shear and moment diagram so that we can quickly identify where in the model is critical and where we need to do additional analysis, and make sure that we're not missing those spots. Nonlinear gaps also have a number of little tricks. Here's a little model. This is actually a little structure out of a standard structural mechanics book. This particular problem is out of Beer and Johnson, and I also give it to my classes where you have a little series of a couple different things, a little gap, and you can predict this easily by hand. First year or second year undergraduate can do this kind of calculation by hand and then compare to the NASTRAN results. Make sure that they're using gap elements correctly, and that's just one of many models we can do. If we're talking about nonlinear analysis, material nonlinearity, there's a few different ways to do this. Once again, these tools can be difficult to use correctly, and the only way to do this correctly is to first make sure you understand what NASTRAN can do, how it works, what are the limitations of each of these, whether we're using a 2-point stress strain curve or a multi-point, or where we're trying to do elastoplastic kind of analysis, and how to calculate those parameters that get fed in order to do this correctly. We have to do this on a simple element that is predictable and understandable, and then build into more complicated models. This is the purpose of my NASTRAN primer that I wrote a couple years ago here, was to break it down to the simple kinds of checks. And right now that is still only covering a few elements to kind of get people started and my students started. I plan to add more to that. But the basic idea is try to get us all thinking, making sure that we're all masters of NASTRAN, understand how these elements work before we go and use them in the bigger models. Another one, linear buckling analysis. So once again, a little simple model. Now this is not a single rod. In order to get buckling analysis, you're going to need a bunch. And this would be, 4 elements would be one of the fewest. And looking at how buckling works, going from like a 4-element model of a certain length to like a 100-element model of the same length is a good way of understanding what coarseness or fineness of a model that we need in order to get accurate results. Learning how to spot what the critical eigenvalues are and how to use those to predict buckling behavior. We can predict the buckling behavior often using something as simple as Euler's equations with the appropriate end constraints, and then we can compare to those eigenvalues coming out of NASTRAN, learn how to write margins of safety. We can check all of that at a small detailed level prior to going on to others. As we can practice this out with little simple models like this, we can go and look at the different eigenvalues where we go from the first mode to the second mode to the third mode, and understanding which of these might be real modes and which of these might be imaginary modes. It's really hard to do when your model gets complicated, but if you first do that on a small little element by element basis, you can build that understanding and that competence so that when you get to the bigger model, you know that you're getting the results you want. shears. So shear elements in NASTRAN are pretty cool. They have some serious limitations or tricks and traps of how they work. It's critical that anybody doing shear panel analysis understands how this NASTRAN works, how it's going to give you shear flows, it's going to give you kick forces, and it's going to be really easy to lose those kick forces when you're doing your analysis if you don't understand how that NASTRAN element works and aren't experienced in applying that. So this is just a little graphic showing kind of how you can map those shear flows and kick forces onto the imaginary rods that surround the panel and superimpose those onto the other elements around the panel so that you can understand your analysis and the elements that NASTRAN is giving you and not misuse or cover up your mistakes by a pretty picture that people just plain old can't understand. So these are some of the ideas that I wanted to talk about, and I'm hoping that this maybe triggers you or inspires you to figure out a way to make your analysis better. Go out there and be great.